Alright everyone, so I'm going to apologize right now. My kids are in the background because I'm making this video at home because I was in meetings all day today and couldn't make it at school. This is the last workshop video though on applications of math for the project. This is the analysis of your graph. So as you see before you, I have a graph here with a couple of points. Keep in mind, each of these points represents a time and a velocity. Of course, I made these up so there are no decimals, but for yours, you have a whole bunch of times and velocities. Now, there are a couple things that I need to do with respect to my analysis. Thing number one is going to be determine if this is a graph that is growth or decay. You can automatically tell that from your b value of your equation, which is why you found it. So for step one in the analysis, I would say, hey, listen, this is a growth because my b value equals whatever number it turns out to be, and that b value is greater than 1. Since everybody's velocity is increasing with respect to time, every single person's growth or b value should be greater than 1. The second piece of analysis with respect to this is going to be to determine your intercepts. So for number 2 here, I'm going to put intercepts. And this one's actually really easy because if you really think about it, with respect to the graph itself, you also have an asymptote that should be right here on the x-axis. That means that there cannot be an x-intercept because it doesn't make sense for you to have zero velocity because that would mean that you're not moving at all. And we're only determining this as a motion of moving. So then I go to the y-intercept. Now I could go back to the whole idea of, hey, to find the y-intercept, that means I set my x equals 0 and solve. Or I could realize that on the graph, this y-intercept, going back to our previous workshops, represents something. That point represents our initial value. Now specifically, if you go back to finding your equation, we had to find our b value, which gave us number 1. We also had to find our a value, which gives us number 2. So if my equation, let's say, was f of x equals 1.2 times 1.3 to the x, that 1.2 right there, let's say this is the equation of this graph, would be my a value, which is my y-intercept. So in this case, I know that my a value is 1.2. That would be from my equation. I then know that my y-intercept is located at 0, 1.2. Super easy. That's my start value. Hey, 1 second, sweetie, okay? I have to finish one more thing. All right, sweetie?
I made Sophia sparkly.
Ooh, I'm glad you made Sophia sparkly. Good job. Sorry about that. Okay. Life as a parent is fantastic. So, last thing I'm going to do here is step 3, and that's the thing that then connects back to the physics of the thing. So step 3 is going to be the acceleration. Now, the really cool thing with acceleration is that you can actually calculate it from the graph or from the table of points that you gathered, but I like to have both so that I can explain both to you. So what I'm going to do here on my graph is in green, I'm going to go ahead and connect 2 consecutive points here. Now keep in mind, each of these points represents a time and the corresponding velocity. So by connecting this line right here, what I'm actually doing is find the slope of the line, the rise over the run. So if I look at these 2 coordinate points here, I see that my y values are 2 and 1. So to find my rise, that'd be 2 minus 1. My x values are 1 and 3. So to find my run, that would be then, let's see here, 3 minus 1. And I get that my slope here is 1 over 2. Okay, well, here's the thing. This represents the slope of that line between those 2 velocities, which is great. One could say that this represents also the change in velocity over change in time, which happens to be the acceleration. So what we just did here is something called the difference quotient, which I'm going to write down here. So difference quotient. And the difference quotient says that if I have 2 points that are on a curve, I can approximate the slope of the line of a point by connecting them on that curve with a straight line. So basically saying, instead of trying to figure out what this curved red portion is, by finding the slope of the green line, that's a great approximation of the average acceleration. So for the physics standpoint, here's all you need to do. For acceleration, you're finding a whole bunch of difference quotients or slopes between each consecutive set of points. In this case, between 1, 1 and 3, 2, the average acceleration was 1/2. Between the points 3, 2 and 6, 4, the average acceleration is going to be something different. Hopefully, since this line is steeper, it's going to be a larger acceleration. So what you need to do is compile now a list of all of your separate accelerations by finding the slopes of these lines that connect each of your consecutive points. That now ends our analysis workshop. We are at 5 minutes and 20 seconds. If you have questions, please feel free to email me.